we've talked about different ways to classify chemical reactions. We talked about precipitation, we talked about acid-base, gas evolution, oxidation reduction, and a very specific form of oxidation reduction called combustion, where we have oxygen involved. These are all certainly different ways to look at and classify the different types of chemical reactions, but the way that we classify them in this manner has to do with like the things that form or what you witness or observe out of the reaction. There's another way to classify chemical reactions. You get overlap. So what I'm about to show you, this applies to certainly all the different types of reactions, but there's another way to look at it, and you could group them differently as well based upon what the atoms actually do in the reaction. Okay, for example, say you take two things together, like magnesium and oxygen. So Mg plus O2, and you get MgO. Okay, 2MgO is what it would be, right? 2Mg plus O2, 2MgO. If you had oxygen and magnesium reacting to form magnesium oxide. Instead of saying that that is a combustion reaction, or instead of saying it's an oxidation reduction reaction, that certainly is valid. You can still say that. But another way to look at it is, we call it a synthesis reaction, whenever you take two parts together and make them a whole. Okay? So if you see that, especially if there's like one product on the right, and the reactants are all involved in the formation of that one product, we call that a synthesis reaction. And of course, the opposite of that would be a decomp reaction, decomposition, whenever you have something that's then sort of breaks apart into its constituents. So these are easy. A displacement or a single displacement reaction. The point of going through some of those exercises in the lab was to show you these different types of reactions. That was the whole point. But you were supposed to do a synthesis reaction. See what I meant? Do a decomp. Do a single displacement. Do a double displacement, and realize what you are doing. In the case of a single displacement, what you have is, say, I don't know, say this is copper chloride. Copper 1, copper 2, doesn't matter. Some sort of copper chloride, and this is iron. And you mix them together, and what you could have is the iron could bond with the chloride, say it was insoluble or whatever. Point being that, say if it was ionized, it would form something positive. And if this formed something positive and this was something negative, realize that A and B could switch places, is what this is saying. Okay? If they switch places and there's one thing by itself and it only bumps out one thing like this, we call that a single displacement, or just a displacement reaction. Versus if we had a situation, what's called a double displacement reaction, where you see this happen. There's actually two sets of partners instead of one partner, one by itself. If there's two sets of partners and both of those switch partners, you get what's called a double displacement reaction. So these are also valid ways to explain what type of reaction that we're dealing with. Sorry, so if we go back here, we got another flow chart. So we can also break down chemical reactions not only into the things that we talked about, but another way to look at it is synthesis, decomp, single displacement, double displacement. So be able to recognize that. So two or more reactants come together to form one product. We call that synthesis. So there's one. Carbon monoxide reacting with oxygen to get carbon dioxide. You can see how these two come together to make one unit over here. We call that a synthesis type of reaction. We could also say that's a combustion reaction, so we could double classify it if we wanted to. Same thing here. Okay, synthesis reaction. In this case, also a synthesis, since all these things are actually tied up into one molecule over here. Decomposition is just going to be the opposite. Usually, in order to achieve a decomposition, you're going to have to supply energy to that. Like you're going to have to heat it up or bombard it with light waves or something like that to cause it to decompose and to cause it to fall apart. Usually, it's only going to be one reactant to make two or more products. Like if you take iron 3 chloride and run electrical current through that, you can actually decompose it into iron chloride and iron 2 chloride and chlorine gas. That would be a decomposition reaction. Same thing here. With mercury 2 oxide, same thing here with ozone. This is actually what happens up in the atmosphere. O3 is ozone. With HV, remember what HV stands for? I told you about it. There's certain things I told you could be written above this. This means what right here? That's heat. That's electricity, right? This is light. So it's like a photo effect. Energy can be absorbed from the light that's passing through the atmosphere, and it gets absorbed by these ozone molecules and can get converted into oxygen as a result. Okay? So those are all decomposition reactions. I talked about that already, how you could set up a circuit involving water and an electrical current, and you could actually separate the oxygen and the hydrogen from water. That would be a decomposition reaction. In the case of a single displacement, take zinc and hydrochloric acid. If you mix those two things together, what can happen is these guys can switch places. Okay? Now keep in mind what would happen when solid zinc would start to disappear. It looks like it will be dissolving in this acid. But realize that those atoms of zinc, if you have hydrochloric acid and you drop zinc in it, that zinc doesn't disappear. All it does is it spreads farther apart from the zinc atoms that were holding it together in a solid, and it goes out into solution. And water molecules get between all those zinc ions and everything else. So they spread out, and they're still there. So we call that zinc chloride just by sticking it on with this chloride, but realize this is not a solid. Remember what this actually means when it's aqueous, is these guys are just ions and they're floating around. Okay, we've just kept track of them by sticking them together. What would happen in that case is hydrogen would be released. And when hydrogen is released, it's a diatomic molecule. It doesn't like to float around by itself. So if it can float around, what it will do is tend to join with another hydrogen, since there's really nothing else for it to want to hook onto in this case. It'll join with itself, and when it does, it forms hydrogen gas, and then it bubbles. So that's why when you drop zinc and hydrochloric acid, it starts to disappear, and also there's a ton of bubbles that start to come up. So when they switch places, it's a single displacement. That displaced this one. In the case of iron 3 oxide, and aluminum, they can displace each other, okay? And as a result, you can extract solid iron from this process. Okay? You can get iron by itself and form aluminum oxide, which is sort of like a white powder. Like if you have aluminum siding, it's that white powder that forms on the outside of your house. That's aluminum oxide. So you can see where these guys switch places. Okay, so that's single displacement. Same thing here. Now remember what I said about water and chemical equations. One way to think about it so that you can keep track of what goes where is think of water, instead of think of it as H2O, what did I say? Do you remember? HOH. If you think of it as HOH, you can see where there's a hydrogen ion and a hydroxide ion together. So if you have HOH, you know that this Na can bump out one of those H's, right? And if it bumps out an H, because the Na has to go with something negatively charged, right? So it's not going to hook up with H. It's going to have to hook up with O. So if it does, in this case it's OH, because it's H in a hydroxide ion. So the hydroxide and the sodium can hook up and form that, and that leaves hydrogen by itself to form that gas that you see there. Okay, this is similar. Did we do was that the lab you did with her? You get copper out of solution? Is that what that last lab was? You didn't do that one yet? You didn't do that part of it? One of the labs that we were going to do is to take like a copper solution, like a copper sulfate, whatever solution, and put a different metal in with it so that that metal can basically do this. Well, actually you could use zinc. Say you have a copper chloride solution, probably like a bluish color. And say you wanted to get the copper out of it, because realize like when you're mining metals and stuff like that, a lot of these metals are tied up in ores. You've heard of that term before, right? Like this mixture of different ion or different types of metals present. Say you want copper. You know, you don't go out in a mine and just see little lumps of pure copper sitting around. It doesn't work like that. It's too reactive. So it'll be mixed in with a bunch of other stuff. What you can do is treat it with acid, and when you treat it with acid, you dissolve all those ions and put them in solution. That's what acid can do to metals. Puts it into solution. If you put it into solution, how are you going to get, for example, now how do you get those copper ions that are floating in solution? How do you get it back out of solution to make solid copper? One way that you can do it is take this and like take a sample of metal of something that's, I'll talk about probably if you ever take Chem 2, that will displace copper in a reaction. Okay? If you put this in here, what you can cause to happen is, see what forms over here. If you look at the reaction, it would be CuCl2 plus Zn. Zn and Cu would switch places. Zinc and copper would displace one another. And what you would do is create the metal that was on the zinc, this zinc plate, would go down in and form ions, zinc ions and chloride ions floating around, and kick out basically copper. Copper would start to deposit on this zinc strip that you had. And you could actually collect solid copper formation, copper metal right here. We were going to do that lab. I don't know if we have time to do it or not. Anyways, that's an example of a displacement reaction. A double displacement is when we just switch two of them up. I didn't have an actual chemical equation up here, but you can figure it out. If you have, this is positively charged, this is something negatively charged, positive, negative, take them, switch them. Take X and A and switch partners, and you got a double displacement reaction. You should be able to recognize that pretty easily. Okay, so your precipitation, your acid-base, your gas-evolving reactions, you will see that when you start classifying those, you could also classify those as double displacement reactions. Okay? Depending on the choices that I give you is going to depend on what your answer will be. I'll never give you a chance where, if I only have A, B, C, and D, I'm not going to list 2 of the possibilities there. Only one of them will be the answer, so you can figure it out. All right, Chapter 8. We got some ground to cover. If I don't get it done, then we'll figure out. We have a test scheduled for Thursday, right? So if I don't get this done, then I'll let you know at the end of the lecture what I'm going to do about the test. We'll see.